You know, for as long as we've been human, we've looked up at the stars and just wondered. It's a question that connects every single one of us across every culture, every generation. And today, we're going to dive into how science is planning to get a real, data-driven answer to that very old question.
Are we alone? I mean, it's got to be one of the biggest, most profound questions we can possibly ask. But you know what's wild? It's not just for philosophers anymore. For the very first time in our history, we are actually building the tools to go from just speculating to doing real experimental science. And the main framework scientists use to even begin to tackle this giant question is the Drake equation. The best way to think about it is like a cosmic recipe. It takes this huge mystery, how many chatty aliens are out there, and breaks it down into a bunch of smaller, more bite-sized ingredients.
Now here's the really cool part. We've actually made incredible progress on the first few ingredients in this recipe. Thanks to decades of astronomy, we have some really solid numbers for how fast stars are born, what percentage of those stars have planets, and even how many of those are rocky worlds in that just right Goldilocks zone.
I mean, seriously, what used to be pure guesswork is now getting filled in with hard data from amazing telescopes like Kepler and TESS. We now know for a fact that planets, especially the small rocky ones, are super common. But this is where the known facts stop, and the biggest question of them all kicks in.
And that brings us to the very next term in the equation, FL, which stands for the frequency of life. This is the giant flashing question mark hanging over everything. It's the one variable where, right now, our best guess is no better than a total shot in the dark.
So what does FL actually mean? It's the percentage of planets that are suitable for life, where life actually gets started. Is it like 100%? 1%? Or is it so mind-bogglingly small that Earth is basically a statistical miracle? We just don't know. And this single number is what separates a galaxy buzzing with life from one that's just sterile and empty.
Okay, so what if we could actually measure it? Well, that's the whole idea behind a pretty bold proposal called the Drake mission. Its entire purpose is to get the first ever experimental measurement of FL, to finally turn this critical variable from a wild guess into a real statistical boundary.
So the plan is this. Build a dedicated space telescope that would just stare at rocky planets in the habitable zones of stars near us. It would use a really cool technique called transit spectroscopy. Basically, you watch for the tiny dip in starlight as a planet crosses in front, and you analyze how the planet's atmosphere filters that light. You're looking for telltale signs of life, biosignatures like oxygen or methane.
Now, you might be thinking, hold on, why only those specific stars, right? M dwarfs are way smaller and cooler than our sun, so why not look for another Earth around another sun? Well, turns out there's a very, very practical reason for it.
It all comes down to the M dwarf advantage. Just look at this. On the left, for M dwarfs, planets whip around them in just a few days, not a full year. That means we get to see way more transits way more often. Plus, because the star is smaller, the atmospheric signal from the planet is actually bigger and easier for us to read. Compare that to a sun-like star on the right. The signal is tiny and way harder to detect. It's just the most efficient way to get the job done.
But, okay, we gotta have a reality check here. The odds of a planet's orbit lining up just perfectly so we can see it transit, it's low, like around 1%. So what that means is, even with all these missions finding new planets, our total sample size of worlds we can actually study this way is going to be pretty small. We're talking maybe only a few dozen in the next decade or so.
And this brings us right to the heart of the matter. Can looking at a tiny sample, let's say 50 planets, really tell us anything profound about how common life is across the entire Milky Way with its hundreds of billions of stars? It kind of feels like trying to understand all the world's oceans by studying just one drop of water, right?
But here's the amazing part. According to some very detailed statistical simulations, the answer is a huge, resounding yes. It turns out the power of statistics is so incredible that even a small, well-chosen sample can give us powerful scientific limits and start to replace that giant question mark with an actual number.
Okay, so let's walk through this. Imagine the Drake mission launches, it checks out 50 of these promising planets, and it finds nothing. Zip. 0 biosignatures. A totally silent cosmos. Now that might sound like a failure, but scientifically, it is a monumental discovery. Because what that result tells us is that we could then say with 95% confidence that the real frequency of life in our galaxy is probably less than 6%. See?
Finding nothing tells us that life isn't just popping up on every wet rock out there. It proves that life is rare. And that discovery, all by itself, would be one of the most profound in all of human history.
All right, but let's flip the coin. Let's imagine the other outcome. The mission surveys those 50 planets, and this time, boom, it gets hits. On 5 of them, the atmospheric data is just screaming biosignature. We find not one, but multiple examples of life beyond our solar system.
So what would that tell us? Well, with that data in hand, we could say with 95% confidence that the true cosmic frequency of life, that FL number, is somewhere between 3 and 20%. For the first time ever, we would have a measured value. The Drake equation would get a real number plugged into it based on actual evidence.
And that is the absolute beauty of this idea. It doesn't matter if we find 0 life or 10 living worlds. The result is completely transformative. We win either way. We finally change the search for life from a philosophical guessing game into a real data-driven science.
So let's zoom out to the big picture here and what this all means for the entire field of astrobiology. Because this isn't just about one more mission. This represents a massive shift in how we even approach the question of life in the universe. This would literally be the moment the search for life becomes a true experimental field. It would be as important to astrobiology as the invention of the telescope was to astronomy, or what the microscope was for biology. We'd finally be moving from what ifs to what is. And as Subhajit Sarkar, the author of the paper, puts it, this whole mission concept is a viable approach. This isn't science fiction. It's an achievable plan to carry out what could be one of the most important experiments of all time.
And that leaves us with one last really fascinating thought to chew on. Once we do this experiment, once we finally get a number for FL, which answer do you think would change our world more? Discovering that the cosmos is silent and that we are profoundly special, or discovering that the universe is just humming with life and we're just one voice in a vast cosmic choir? Something to think about.